Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals x plus 1 squared times 2x plus 3 to the negative 2. The first thing to do is find the domain. F of x equals x plus 1, a polynomial, to the positive 2 power, the domain will be all real numbers, times 2x plus 3, another polynomial, to the negative 2 power, which means it can move to the denominator to become positive 2 power, and the domain requires that whatever is in the denominator cannot equal to 0. For here, what is in the denominator will be 2x plus 3 to the positive 2 power, and the domain requires that this does not equal 0. We can solve for x here by taking the square root of both sides. The squared and the square power will cancel each other out, so 2x plus 3 does not equal, and the square root of 0 is 0. We can now subtract 3 from both sides, so 2x does not equal negative 3, and divide both sides by 2, so x does not equal negative 3 halves. The domain will be all real numbers except negative 3 halves. So it'll be all real numbers to the left of negative 3 halves, negative infinity up to negative 3 halves, not including it. Union, all real numbers to the right of negative 3 halves, so it'll start again at negative 3 halves, not including it, round bracket, up to positive infinity. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F of x is a product of two expressions, so the derivative will require the product rule. F prime of x equals the derivative of the first. It's a power rule. Bring down the power, leave the inside alone, subtract 1 from the power, multiply by the derivative of the inside to complete the chain rule, times the second left alone, plus the first left alone, times the derivative of the second. It's a power rule. Bring down the power, leave the inside alone, subtract 1 from the power, and now be negative 3, and then multiply by the derivative of the inside to complete the chain rule. For the first term, we can put all the constants together. Everything's multiplied here. 2 times 1 is 2. There's an x plus 1, and there's a 2x plus 3 to the minus 2. For the second term, we can put all the constants together. We have a negative 2 times a 2, which is a negative 4. We can move it out front. There's an x plus 1 to the power of 2, and a 2x plus 3 to the power of negative 3. If we were to take the second derivative from here, we will need a product rule for the first term and a product rule for the second term. That can be a little messy, so we can attempt to factor the first derivative before we take the second derivative. Perhaps that will simplify it. There's a common factor of 2 between the coefficients. There's a common factor of x plus 1. We have a power 1 and power 2. We can factor out the lower of the two powers, so we can factor out x plus 1 to the 1. And there's a 2x plus 3 to the negative 2 and to the negative 3, and we can factor out the lowest power, which is the negative 3. Factoring out a 2, that'll become a 1, that'll become a negative 2. Factoring out an x plus 1 to the first power, factoring is dividing, dividing is subtracting exponents. We have x plus 1 to the 1 power here, subtracting 1 from will become a 0, anything to the 0 is a 1, that whole term will become a 1. Subtracting 1 from the 2, it'll become a 1. Factoring out a 2x plus 3 to the negative 3, we'll be subtracting a negative 3, which is equivalent to adding a 3. If we add a 3 to this, it'll become a 1. If we add a 3 to this, it'll become a 0, and anything to the 0 is a 1. There's what we'll have left. A 2x plus 3 minus 2 times an x plus 1. So f prime of x equals, we have a 2, we have an x plus 1, we have a 2x plus 3 to the negative 3, and in square brackets we have a 2x plus 3. It just has a 1 outside of it that's implied to be there, so we can remove the parentheses, times it by 1, which will remain itself. And then we have a negative 2 that can distribute in to the x plus 1, giving negative 2x minus 2. So we have 2 times x plus 1 times 2x plus 3 to the negative 3. And then in square brackets, the like terms can combine. The 2x and the negative 2x will cancel, and then 3 minus 2 is a 1. That 1 can move out front with the 2, and it'll be 2 times x plus 1 times 2x plus 3 to the negative 3 power. We now have just a single product rule for the second derivative. We can now find the second derivative, f double prime of x equals. It is again a product rule. We have a 2 times the derivative of the first, which is a 1, times the second left alone, 2x plus 3 to the negative 3 power, plus the first left alone, so 2 and x plus 1, times the derivative of the second, which is a power rule. Bring down the power, leave the inside alone, subtract 1 from the power, and then multiply by the derivative of the inside to complete the chain rule. For the first term, we have 2 times 1, which is a 2, and a 2x plus 3 to the negative 3 power. For the second term, we can put all the constants together. We have a 2, a negative 3, and a 2. 2 times negative 3 is negative 6, times another 2 is negative 12. We also have an x plus 1 and a 2x plus 3 to the negative 4. We want to fully factor the second derivative. There's a common factor between the coefficients, 2 and 12, of 2. So we can factor a 2 out. And then there's a 2x plus 3 to the minus 3 and a 2x plus 3 to the minus 4. We can factor out the lower power of the 2. That will be the minus 4. Factoring out a 2, that'll become a 1. That'll become a minus 6. Factoring out a 2x plus 3 to the minus 4. Factoring is division, and division is subtraction of exponents. We'll be subtracting a negative 4, which is equivalent to adding a 4 to each of the exponents. Negative 3 plus 4 will become a 1. Negative 4 plus 4 will become a 0, and anything to the 0 is a 1. There's what we'll have left, a 2x plus 3 minus 6 times an x plus 1. So our second derivative, f double prime of x equals, we have a 2. We have a 2x plus 3 to the negative 4 power. And inside the square brackets, we can remove the parentheses from the 2x plus 3. There's a 1 implied that would multiply and doesn't change it, so it'll be 2x plus 3. There's a negative 6 that can distribute n, giving negative 6x and minus 6. So we have 2 times 2x plus 3 to the negative 4 power. And in the square brackets, we can combine like terms together. 2x and minus 6x will be a negative 4x. And 3 and minus 6 will be a negative 3. We can factor a negative out of the square brackets. It can move all the way to the front with the 2, so it'll be negative 2. 2x plus 3 to the negative 4. Square brackets can now be written as parentheses, and we will have, after factoring out a negative, positive 4x and positive 3. We have a negative power. It can move to the denominator to become a positive power. We have a negative 2 that will stay in the numerator. We have a 4x plus 3 that will stay in the numerator. And we have a 2x plus 3 to the negative 4 that will move to the denominator to become a positive 4 power. We now have the second derivative written as a single fraction. All powers are positive, and it is fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. Starting with the numerator, we can divide both sides by a negative 2. We can subtract 3 from both sides. And we can divide both sides by a 4. And now the denominator. We can start by taking the 4th root of both sides, because the 4th root and the 4th power cancel. And the 4th root of 0 is 0. We can subtract 3 from both sides and divide both sides by a 2. We will now check to see which of these are in the domain. The domain is all real numbers except negative 3/2. Negative 3/4 is a real number. It's not negative 3/2, so it is in the domain. We keep it. It is a candidate number. Negative 3/2 is not in the domain. We cross it out. So we have one candidate number. We can now draw a domain line, a line representing the domain. The domain has no left end, because it starts at negative infinity, and no right end, because it ends at positive infinity. It is broken up because it cannot include negative 3/2. And that's because negative 3/2 is making the denominator equal to 0, and it can't be that. Therefore, x equals negative 3/2 is actually a vertical asymptote, breaking up the domain. So at negative 3/2, we have a vertical asymptote. That'll be indicated by a dashed line. We can put all candidate numbers on here. We have a negative 3/4. 3/4 is less than 3/2 because it has a bigger denominator. Negative 3/4 will therefore be greater than negative 3/2 by being less negative. So it'll be to the right of it. The domain interval was broken up into 2 parts. Putting the candidate number in here, we now have the interval split into 3 parts, 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to negative 3/2, we can pick negative 10. The next interval, negative 3/2 to negative 3/4. 3/2 is 1.5. It's greater than 1. It's less than negative 1. 3/4 is a fraction that's less than 1. Negative 3/4 will be greater than negative 1. Negative 1 will be between negative 3/2 and negative 3/4. So we can pick that as the test value. And then for the interval negative 3/4 to positive infinity, we can pick 0. We can now test the concavity of each of the intervals by plugging the test value into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. Therefore, the best version to use is the fully factored version. That's this version here. Now, a couple things about this. First of all, the denominator is to the fourth power, an even power, and anything raised to an even power, as long as it is not a zero, will be a positive number. Therefore, that denominator is a positive number always. In the numerator, we have a -2 we want to be sure to account for. But only the numerator will matter here, since the denominator is always positive. Plugging in -10 in to the part of the second derivative that matters, 4 times -10 is -40, plus 3 is a negative number, times a -2 is a positive number. We have a positive second derivative. This corresponds to concave up. Plugging in a -1 to the portion of the second derivative that matters, 4 times -1 is -4, plus 3 is a negative number, times a -2 will be a positive number. We have a positive second derivative. This corresponds to concave up. Plugging in the test value of 0 into the portion of the second derivative that matters, 4 times 0 is 0, plus 3 is a positive number, times a -2. Negative times positive is negative. We have a negative second derivative. That corresponds to concave down. So we have concave up happening from -infinity to -3/2, and then union, because it's happening again from -3/2 up to -3/4. We cannot combine those intervals together because the -3/2 is not included in either of them. That's why it has a round bracket on them. It's actually a vertical asymptote. So those are two separate intervals. We have concave down happening from -3/4 up to positive infinity. X equals -3/2 is not a candidate number, it's a vertical asymptote. The only candidate number is the -3/4. Right at the candidate number of -3/4, the concavity changes from concave up to concave down. That makes x equals -3/4 be an inflection point. So we have an inflection point with an x-coordinate of -3/4. It will have some corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -3/4, which will be -3/4 plus 1, quantity squared, times 2 times a -3/4 plus 3 to the -2 power. So this will be -3/4 plus, we need a common denominator, 1 can be written as 4/4, and then squared, times 2 times the -3/4 will be -6/4, or canceling the 2 with the 4, -3/2. So we have a -3/2 plus a 3, which we can get a common denominator by putting it over 2, multiplying by 2/2. It'll be a 6/2 to the -2 power. -3/4 plus 4/4, adding the numerators, -3 plus 4 is a 1. We have 1/4 to the power of 2. And we'll have a -3/2 plus 6/2. Adding the numerators, -3 plus 6 is a 3/2, and it'll be to the -2 power. 1/4 squared, we can square the 1, that's a 1, and square the 4, that's a 16. 3/2 to the -2 power, we can reciprocate it. It'll be 2/3 to the +2 power. This is 1/16 times, we can now square the 2, that's a 4, square the 3, that's a 9. The 4 and 16 can reduce with each other. So we have a 1 over 4 times a 1 over 9. Multiplying the numerators, 1 times 1 is 1, and denominators, 4 times 9 is 36. We have a corresponding y-coordinate of 1 over 36. So we have two intervals of concave up, one interval of concave down, and a single inflection point at -3/4, comma 1 over 36.